Dear students, I, Mr. Vishal Shah, Assistant Professor, Krishna Institute of Pharmacy, Karad, once again welcome you all to this session of Pharmaceutical Organic Chemistry. Here in this video, we are going to discuss about the last part of Baeyer strain theory. In previous three videos, we have serially covered about whatever the assumptions that Baeyer has proposed. Also, we have seen what is the meaning of angle strain, how much angle strain is present in the different cycloalkane examples. Also, we have seen how the certain things that Baeyer has proposed regarding the stability of the cyclopropane and cyclobutane that can be confirmed with the help of the heat of combustion study in previous videos. In this video, we will discuss about the orbital angle strain theory, where with the help of the orbital picture diagram we could understand what things Baeyer has proposed. Also, we will see the advantages and limitations of Baeyer strain theory. So let's begin this our today's session. Before that, we will see what are the learning outcomes of this session. Means after watching this video, what you should understand. You should be able to explain what is the meaning of Baeyer strain theory. You should understand the role of the heat of combustion to study the stability of the cycloalkanes. Also, you should be able to explain the advantages and limitations of Baeyer strain theory. So let's begin. Now, what orbital picture of angle strain theory means? What is the orbital picture of cyclopropane? It gives us information. Already we know that for a bond formation, effective atomic orbital overlap is required. Now, what is the meaning of effective atomic orbital overlap? If orbitals that are involved, they are completely overlapped on each other, then only there will be formation of a perfect bond will take place. For a carbon atom in a molecule, if it is sp3 hybridized, then the bond angle must be at 109.5 and precisely it must be 109.28. At that angle, the orbital overlap is maximum. This is the reason for highly stable compounds like alkanes, then cyclohexane, which is also having sp3 hybridized carbon atom. So in this case, when the bond angle is maintained at the tetrahedral geometry, then the orbital overlapping is maximum, and at that instant that particular compound will be highly stable. For an open chain compound, when carbon is connected to other two carbon atoms, and if it is a sp3 hybridized, then this utilizes the hybrid orbitals to form the bonds. For example, here you can see the picture. Here first we will consider these two pictures where you can see here this particular orbital is completely overlapped on this second orbital. This type of overlapping is known as the good overlapping. If this type of overlapping is there in the bond formation, then that particular bond will be more stronger, more stable, and in that case carbon will maintain its tetrahedral geometry. Now in this case, if you see, there is not complete overlapping, only few portions, some portion of that particular this orbital is overlapped on this particular orbital. So in this case, that particular compound is not having a perfect picture, and the bond formed by such type of overlapping is not strong, and the compound will be little bit unstable depending upon how much amount of or the extent of the overlapping is present. Here this type of bonding, that is the not, or you can say incomplete overlapping, is the case in case of the cycloalkanes which are not stable. For example, here you can see, suppose these are the two carbon atoms, or you can say carbon 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 bond. If this bond is 109, then tetrahedral geometry is measured or maintained. As we know, if we take the example of cyclopropane, here we see that in case of cyclopropane, the bond angle is only 60 degrees Celsius. not it's a 60 degree. So in order to achieve the tetrahedral geometry, it requires round about the 49. Already we have seen. If we consider it at the one end, then 24.44 degree, that much amount of angle is required to get the tetrahedral geometry. Means this much amount of strain, that is the 24.44 degree, is the strain that is present in the cyclopropane. So this picture clearly gives us an idea about the how the strain is present on that particular cyclopropane ring. If this carbon atom is present at this particular position, then in that case only, so in case of cyclopropane, as these two carbon atoms are away from the whatever the desired tetrahedral angle is there, that's why these carbon atoms, and in this way these particular bonds are having the strain on that particular carbon atoms, and this strain on each side of carbon atom is 24.4 degree. So in order to maintain the tetrahedral geometry, that particular strain is achieved by the cyclopropane, and that's why the angle is maintained at the 60 degree. In that case, this type of overlapping is not observed, because overlapping, if the complete overlapping is there, then the tetrahedral geometry or the angle is maintained. And in this case, this instead of this type of a picture, here you can see whatever these carbon atoms are there, they are maintaining the tetrahedral geometry. But when they maintain the tetrahedral geometry, here this type of overlapping does not take place. And in order to get these two orbitals to be overlapped, to get this type of a picture, it's necessary that these orbitals should come inwards towards this particular center. And that's why this type of overlapping, that is the incomplete overlapping of orbital, is observed in the cyclopropane, and that's why strain is more. And that's why these particular compounds are unstable, like cyclopropane and cyclobutane. Similarly, we can see the picture of the cyclobutane also, where this angle in cyclobutane is maintained at the 90 degree. So as we go on increasing the chain length, number of carbon atoms that are present in the chain, then that particular stability increases. Cyclopentane is having less strain, due to which it is more stable. For cyclohexane, no strain is present, because Baeyer actually does not able to explain these particular things, but we will study that particular why cyclohexane is more stable, how it maintains the tetrahedral geometry. That two further theories are there where we can see in detail about the cyclohexane. Here just you have to understand that only Baeyer has proposed the things that are correct for the cyclopropane and cyclobutane, and somewhat to the cyclopentane. Rest of the things regarding the cyclohexane, what he has proposed, or the larger ring system, that were not correct and which are justified by the other different theories. So this is about the Baeyer strain theory. So here you can see how the orbitals are overlapped in the cyclopropane, and due to which the angle is maintained at the 60 degree. Now we will see what are the, now here you can see cyclopropane, the bond angle is 60 instead of 109. In this case, carbon atoms involved do not use sp3 hybridized orbital to form the bonds. As a result of this, the bond which formed is weaker as compared to the usual carbon-carbon bond, and that's why cyclopropane is having less stability. Now we will see what are the advantages of Bayer's strain theory, which is also known as the angle strain theory. Baeyer rightly proposed that cyclopropane and cyclobutane are flat molecules, that is the planar molecules, and they are having angle of 60 degree and 90 degree. Those are much deviated from the ideal tetrahedral value, that is the 109.5, precisely 109.28. Hence these ring systems are unstable and easily undergo ring opening reactions. There is much angle strain in cyclopropane as well as the cyclobutane. Baeyer also proposed that cyclopentane is not needed to be planar, but it is planar as in that condition the angle is much near to the ideal tetrahedral angle. So Baeyer has proposed the cyclopentane is not needed to be planar, but it is planar in that condition. The angle is much near to the tetrahedral angle, and that's why it is having more stability as compared to the cyclopropane as well as the cyclobutane. So these are the various things that are correctly proposed by the Baeyer. But also Baeyer strain theory is having certain limitations also. So we will see now the limitations of Baeyer strain theory. Baeyer was not able to explain the effect of angle strain in larger ring systems like cyclohexane, cycloheptane. According to him, these rings are not existing, but later it was found that these rings are also existing, and practically we can carry out the isolation of this particular ring. According to the Baeyer, cyclopentane should be much more stable as compared to the cyclohexane, but practically it is reverse, that cyclohexane is more stable as compared to the cyclopentane, because cyclopentane is having small amount of strain on that particular ring, but cyclohexane does not have any strain because it achieves the tetrahedral geometry. How it achieves the tetrahedral geometry, that we will study in the further different theories. Larger ring systems are not possible according to the Baeyer, as they have the negative strain, but they also exist and they are much stable. So these are the various limitations of the Baeyer strain theory, and also larger ring systems are not planar, but they are puckered to eliminate the angle strain. So these are the various limitations of Baeyer strain theory. So here we have completed the Baeyer strain theory. In next video we will see remaining two theories related to the stability and the reactivity of the cycloalkanes. If you like the content of this my video, you can like my videos, share with your friends, and subscribe to my YouTube channel. Thank you very much.